Okay. Okay, so yeah, go ahead. We have a question. Yeah, I'll try to upload them. Okay, so we're talking about gradient computation this week. So just from the exercises, who managed to kind of generalize or like to train a multi-layer perceptron with the 2 internal nodes from the exercise? Okay, 1, 2. Yeah, maybe. Okay, so a few of them. So the point of the exercise is that even for like a very simple network like what we had, it's extremely annoying to do gradient computation. And so we'll spend this lecture to talk in depth about how to compute gradients. This is the recap from last week. So finally, we kind of dipped our toes into deep learning in the sense that we had like a single hidden layer. It's not very deep, but at least it's kind of 2 matrix kind of multiplications deep. And so one thing that we derived, and so this kind of opened up the door to a much richer family of functions. So with the perceptron, we only had linear decision boundaries, and then even by just adding a single hidden layer, we could show that this is a universal function approximator, and we can basically learn any type of function if we just have enough data. So we can kind of basically increase our hypothesis set to as complicated functions as we want by just adding more and more nodes in the hidden layer. So then we could basically see that, okay, instead of just having linear decision boundaries, what this kind of hidden layer, multi-layer perceptron gives us kind of non-linear decision boundaries. And if you add enough nodes, these kind of become a little bit like curves. And so this is very much in the way. So I don't know. Okay. Can I hide? Okay, whatever. Okay, so then we have basically our non-linearity. So the key issue is that instead of just like stacking linear compositions on top of each other, so the key difference is that we added non-linearities. And so the kind of easiest non-linearity that we talked about is the ReLU, which you can see here. And then at the end of the lecture, we talked a little bit about the like benefit of depth. So it's true that the kind of single hidden layer, multi-layer perceptron can kind of approximate any type of functions, but you need exponentially more and more hidden nodes in order to kind of approximate this function well. And you can see from this that, okay, even with just 1,000 parameters for a deep network, you can approximate a function that for a shallow network with just a single hidden layer, you need like 30,000 parameters. So it's not like you're done, but once you have a universal function approximator. Okay, so then this is just from the exercise. So here we basically have like 2 hidden nodes on the left. And so you can see, okay, it's already not a linear decision boundary. And so this is as you're training, the decision boundary improves, right? But okay, it's not great, right? So it's, but I mean, it's already not linear, non-linear, so that's good. And so now we're adding more and more hidden nodes, and you can see that the decision boundaries become a little bit more complicated. So now it has enough parameters to kind of construct like a almost closed surface, and it can kind of really have a decision boundary that is differentiating between the inner and then you see it's already becoming quite good, right? And so this is what you get by adding more and more complexity in your multi-layer perceptron, even with just a single hidden layer. And so here, this is just another example. So this is the famous 2 moons data set. And so here again, we have just a few nodes. And then as we add nodes, the types of functions that we can express through training become much more complicated. And here again, with 10 hidden nodes, you can actually get a decision boundary that is roughly faithful to what the data tells you. Right? Okay, so okay, the problem is that if you did this exercise, it's super annoying because not only did you have to write like some code in order to implement like what the multi-layer perceptron is as a program, so which is okay, you need to kind of do your linear maps, and then you need to add your non-linearities. But there was a lot of code that is just basically there just in order to kind of deal with the gradient stuff, right? And this is super annoying, and it just becomes more and more and more complicated. And so while you might think, okay, you might be able to do it like for this super short program, it clearly doesn't scale, and it's super error prone. And when I was designing the exercises, also I did have actually a mistake in the solution the first time around. And so that's super annoying, and we need to somehow figure this out. Okay, it's also very limiting because, okay, we have our universal function approximator with the thing on the left. We have our single hidden layer, but clearly, you know, the details matter. So it's not just that you're done. And as we've seen, like the depth versus width, you know, it's like an important distinction where, you know, if you add more and more composition, this gives you much richer functions with fewer parameters, right? And it's not clear that now you're done. Okay, you figured out, okay, you know, having deep networks is better than shallow networks, and now we're done. I mean, both are universal function approximators, and it's not clear that, you know, just having a deep network is fine, right? And so, but the structural, like the internal structure of a neural network is important. And so this is a slide that I showed in lecture 2. So there was this new no free lunch theorem of machine learning. Basically, so there's no way to have like one neural network architecture that learns everything equally well. But you want to kind of add what's called inductive bias. So you want to constrain your hypothesis set to the functions that you want to have, instead of just kind of being able to represent any type of function, right? And so this is what's called inductive bias. Why is it called inductive bias? Because we want to do inductive reasoning where we go from the data to some general concept. And of course, you know, there are many general concepts that could maybe produce this particular set of data. So you need to have some prior beliefs on which functions are reasonable and which functions are not reasonable, in order to, you know, maybe have like some smoothness constraints and so on. Okay, so we want to basically add structure to the search space. And so we basically want to adjust what we kind of consider the hypothesis space to be, to not just have like a universal approximator of all functions, but we want to basically only have like the universal approximator of the desired functions that we want. So if we want, for example, to have like a function that has some symmetry, maybe it's rotationally invariant or translationally invariant, we don't want to search through functions that are not translationally invariant. You know, what's the point? We already know what type of function we want to have. And so this is just like adding noise and adding difficulty to the learning process. And so we want to be a little bit smart about which functions we even admit as a solution. And so while we have this universal function approximator, that's great, but somehow we want a subset of this, but it's not clear that by a subset, by just removing nodes, this is how you implement like a symmetry. You know, it's not clear that this is happening, but we want to somehow have like a general computer program that has like some inputs, has some outputs, has some parameters, and then what we want to have is basically, you know, have this as a search space that we search through with gradient descent. Okay, so actually the reason why this lecture is now happening is that most of the remaining lecture is actually about having smart choices for these functional families or program families that we want to optimize through gradient descent. So if you've heard about in the news, well, convolutional neural networks or graph neural networks, you know, transformers, which drive all of these like language models and so on, they're all like particularly chosen to have like implement some kind of constraint on the function. So they're not universal function approximators, that they implement some kind of symmetry and so on. And so it's not clear that, okay, it was already painful to do like this gradient computation for the multi-layer perceptron. Okay, how do you take a gradient of like a, you know, rotationally symmetric function? Okay, so what we really want is we want to have the gradient of an arbitrary program. So we have our input, which is our data, that produces an output, and that produces the output based on the parameters that we choose for this function, right? And then the entire game of machine learning is to tune these parameters, you know, in order that this type of input-output relation makes sense. And so this is this ability to compute gradients for arbitrary computer programs or almost arbitrary computer programs is one of the big underlying reasons for the success of deep learning. It's kind of one of the secret sauces deep learning, and sometimes goes under the name of differentiable programming. So not only do you want to compute the input and the output, but you also want to be able to compute gradients for any type of computer program that I write, and not only like some kind of function that I stick into Mathematica or something like this. Okay, so let's start simple. So we're considering a simple function. We just okay, we have a very simple program. So let's do differentiable programming. Okay, we want to go from some Rn to some other Rn, where the dimensionalities of the data is different. So we go from X to A, right? And so now what can we say about the differential? So this is very much annoying me. So I don't know how I can hide this. That's crazy. This is here. Okay, maybe let's try it up here. Okay. Okay, so what can we say about the differentials? And so how it's like a small change in X related to a small change in A, right? So what's a small change in the input? What type of change does it produce in the output? Yeah.
I think you can, sorry, just for the I think you can that so you can actually drag it
I think that, yeah, this way it's fine because they're only the heading. Okay, so we're interested. So if the gradient is large, that means a small change induces a large change. If the gradient is small, the derivative, then a small change induces an even smaller change. If it's a constant, there's no change in the output given any change in the input, right? Okay, so basically the differentials kind of scale according to the Jacobian matrix, right? So the Jacobian matrix is like all the partial derivatives for the different coordinates, and so you have n1 input coordinates and n2 output coordinates, and then basically you have a matrix multiplication. You can say that the input differential which is a vector, so all the changes in the different coordinates, you multiply this by the Jacobian matrix, and this gives you the total differential element for the output, right? And so that's basically just matrix multiplication. You have your matrix Jij, which is the partial derivatives of the input of the output with respect to the input, and that maps kind of from the input differential to the output differential, and this is exactly the type of derivatives that we are interested in, right? So basically, in a way, what we want to find out is, okay, what is the Jacobian of any type of kind of map that goes from input to some output? Okay, so now, so that was a bit trivial. So let's see, okay, how do we go about when we have composition? So in composition, we went, so this was kind of one of the points of deep learning, that we compose outputs into kind of more and more complicated functions. And so we want to go from, one space Rn1 to Rn2 to Rn3, and we always have like different functions that go, that map from one input space to the output space. And so now what can we say about the differentials in this case? So in some sense, there's also just one Jacobian matrix, right? So there's some output of the program, which is C, right? And then there's some input, which is X, and there is some kind of Jacobian matrix between the two, right? And so, which is exactly what we're trying to find out. What are the gradients? What is the differential input-output relation between the two? Okay, but then at the same time, so we know there's one Jacobian matrix, but at the same time, we know that there are kind of three maps in between, right? And so actually, each of these three maps comes with their own Jacobian, right? So it's the same, so we apply the same thing that we had in the previous slide, how we kind of go for a single map that goes from one space to another. And then we can just stick in all of these Jacobians together. And so these two things, of course, need to be the same thing, right? So there's just two different ways to express the same type of relationship. And that's just saying that the Jacobian matrix is just the matrix product of all the Jacobian matrices for the individual transitions that you have in your composition, right? And so that's nothing else than just the chain rule, right? So you have the kind of the derivative of C. So C depends only on B, right? So you have the derivative of C to B, and then you have the derivative from B only depends on A. So you have B to A, and then A only depends on X, and so you have A to X, right? And so this is exactly kind of the chain rule, and it's also something that we kind of worked through in the exercise last Monday. Okay. So that's kind of the starting point where we want to start. And so this kind of So there's somehow like a relationship between, okay, what are the details of F, G, and H in our kind of simple program, and what are the derivatives, right? And so there is some relationship, and we're trying to find out what this relationship is. Okay, so basically what our task is, so we want to know the gradients, so we want to kind of know what are the individual entries in these Jacobian, in the Jacobian matrix, so what are the partial derivatives, and so we need to kind of basically find a way to characterize, you know, what the product of the individual Jacobians is. So we know the overall Jacobian matrix is the product of the individual Jacobian matrices, so that's already simplifying it a bit. So, you know, we have some structure. And so we now need to somehow figure out, okay, how can we characterize this type of structure in an efficient way? And so now we'll do a little bit of a detour and talk mostly about matrices, and then we'll come back to the derivatives and apply what we learned to this. Okay, so matrices, so what are matrices? Matrices are basically linear transformations. So if you have a linear transformation, so you had the multi-layer perceptron, this the weight matrix Wij times X, so that was kind of your linear decision boundary, and then the bias was only shifting it, right? So basically, a matrix is just a thing that transforms an input vector into an output vector. And so it's completely defined by the way it does this transformation. So basically, what this means is, so one way to characterize what the details of the matrix is to just slap vectors kind of either from the left or to the right at this matrix and see what comes out. If we slap enough vectors, you know, at this matrix and see what it comes out, even though we might not really know what the details of the vector is, we treat it as a black box. We can, by just doing this many times, we can know what the details are of this linear transformation. And there's only a finite number of things that we need to do in order to fully characterize it, right? Okay, so let's try to do this. Basically, we want to characterize this matrix through just matrix vector products. Okay, so basically, so what this means is, okay, let's say we have our matrix, we have 3 columns. And so now there's a question, okay, what kind of vector can we, so let's say we want to find out what the first column is. What kind of vector do we need to throw at the matrix? So we're only interested, I'm not interested in the green or yellow or red entries. I'm only interested in the blue entries. Yeah. 1, 0, 0, exactly. So because then if you do the matrix multiplication, okay, you will have 1 times this and then 0, 0, 0, those things don't matter. And so you can extract by, I mean, treating it as a black box. You don't need to know what the function is. Let's say you only have a machine that kind of, you know, will implement this matrix vector product for you. By just throwing 1, 0, 0, 0 at it, you will basically recover what the first column of this matrix is going to be, right? And then you can kind of play this game. So what do we need for the second row, for the second column? Exactly. And so you can say, okay, how many times do we need to play this game in order to fully characterize the matrix? We only need to play it 4 times, right? So basically, the number of times, how many columns we have, right? Okay, so we 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, right? So that's great. So basically, okay, without knowing the matrix, by just having kind of imagining we have a machine that can implement the product of a matrix and a vector, we can fully recover what the details of the matrix is without having some kind of table to look up. Okay. Okay, so basically what this gives us is a nice thing. It basically gives us a new way to store or express a matrix in a way that is computationally more or potentially computationally more efficient. Because the only thing that we need is a program that implements this matrix vector product. And actually what, so for example, if you have a sparse matrix, so if the logic on, you know, what the output relationship is to the input relationship is simple, or maybe there are like some 0 entries, and instead of storing these 0 entries, you can actually just write a program that implements this matrix vector product. And then, you know, you're saving memory because you're not saving each of these entries, right? And so it's but you have lost no information because you can just throw like a sufficient number of vectors at this matrix vector product program, and then you'll recover all of the entries that you need, right? Okay, So that's great. So we can store matrices as programs, and so this is important to keep in mind for our discussion later on. Okay, so basically, our ability to compute matrix vector products is totally sufficient to extract any type of information that we need from a matrix. What's interesting is, okay, we do not need to have an explicit matrix. We just need the ability to compute matrix vector products. And we just, in order to recover everything, we just need to do, as many calculations or matrix vector products as we have columns in the Jacobian, or as we have input dimensions, right? So this scales, the number of computation you need to do scales with the number of input dimensions. So in this case, it's 4, right? Okay, so great. So I don't know, that's maybe, something, a little esoteric, but okay, great. Yeah. No, you don't. Because here, for example, on the left-hand side, I don't have the explicit matrix. I just have like effectively the same computation, right? Like I don't have, like, for example, so I only store 2, 3, and 5 here. So they're only constant 2, 3, and 5. I don't store the zeros, right? Yeah. Okay. So there's a different way to do the same kind of game. So we can go the other way around. So, the matrix is a 2-dimensional object. We can either like, yeah. Yeah, so it's useful when it's when it's a sparse matrix, exactly. If it's, but you're not losing anything through this type of construction. Okay, so we can do the same game the other way around. So we can also do a vector matrix product. So you can also multiply vectors from the left-hand side to the matrix instead of from the right-hand side, and you can play the same game. So what do we need in order to extract the first row? So this will now extract different things. So the first thing extracted columns, and this type of construction extracts rows, right? And so in order to extract the row, we do the same thing. We basically slap kind of like an eigenvector, so one of the basis vectors from the left, and then we do the matrix multiplication, right? And then it's the same type of deal. We only pick up this type of entry here, and then we add it with the 0 times these entries, so there's nothing happening here. And so you do this for every column, and then you're extracting the first row, right? You can do the same thing, with the second basis vector and the third basis vector. And it's the same type of thing. By just doing vector matrix products, you can extract as much information as you want from this matrix and fully characterize the behavior of this linear map, right? Okay. So it's the same kind of slide, but just now there's a slight difference. So it's still the same thing, but now it's our ability to compute vector matrix products to extract the information that we need. But now, how many computations do we need to do? Here we need to only do 3 computations, right? So that's maybe interesting to know. So somehow the number of computations, I mean, here it's 3 because we have 3 output dimensions. So this scales with the number of output dimensions and doesn't scale with the number of input dimensions, right? So here we had 3 computations, before we had 4 computations, right? And then you can start to think about, okay, which one is more efficient? Yeah.
So maybe it goes, it makes sense when it's fast, right?
Yeah.
So
Yeah.
counting.
Yeah. Okay, but then there's one additional step where it becomes interesting, which I'll explain in a bit. Okay. All right, so it's the same type of deal. So we can basically, instead of going matrix vector product, we can do a vector matrix product, and then we can write a program, right? And then this can become more efficient, or like generally just need like a black box that implements these vector matrix products, and will generate the right result for you, and you can extract all of the rows from the matrix, all the rows from the matrix that you want. Okay. So now let's see. So we know we're not dealing only with a single matrix, but we're dealing with many matrices, because we have deep learning is composition, and so it's basically a series of functions. And so let's see how we can deal with composition. So basically, let's say we know our overall matrix is the composition of three matrices, right? And so now we need to, our task is to characterize our final product matrix, right? So what do we need to do? Basically, nothing really changed. So we do the same type of trick. We just slap, basis vectors from the right, right? So let's say we want to extract a, column at a time. Okay, so let's see what this looks like. So our task is, okay, we know we have our trick. We want to slap this first basis vector from the right and basically do this computation. Now we can see how we can do this. So we can, so now the question is, okay, we're supposed to compute this, right? And there's a arbitrary or like a ambiguity. How do you compute this? Do you compute first M3 times M2 and then this times M1 and times E1? Or do you compute M1 times M2 times M1 times M3 and then times M1? So there's many versions on which kind of order you want to go. But it turns out, and this is maybe also the answer to your question, it turns out that going the matrix vector product way from right to left is the most efficient way to do it if you have this relationship that you have many input dimensions and a few output dimensions, right? The other way around, if you have a few input dimensions and many output dimensions. Okay, so basically we want to go, so kind of internally computing these matrix products is much more costly than just doing the vector product as we go. So let's see how this works. So we are slapping our vector from the right, and now we're just doing this thing. So we do a matrix vector product, and it's totally fine. The only thing we can do, we don't know the matrix, we just know how to do a matrix vector product, but it's totally sufficient to do all of this. And so we go, okay, now we have this, right? So how many output dimensions do we have? So we have two rows here, one kind of column vector. And so the output dimension is going to be two-dimensional, right? So that's just matrix multiplication. And now we can just go on, right? And so the only thing that we ever needed to do is we didn't even need to know how to multiply general matrices. We only need to know how to multiply matrices and vectors, which is a more efficient computation. Okay, so then we can do this. And then, okay, we have many output dimensions in this case. Okay, great. And then we have our last piece, and then we have our column, right? So let's do this again. Oops. Okay, we slap our vector from the right-hand side, and just we go, and it's only matrix vector products. The only thing that we ever needed to do is matrix vector products until we are dead, right? Okay, great. So excellent. It's we just need to know the matrix vector product of these individual pieces. Okay, but then we can also go the other way around, right? And so now it's the same type of game, but we just go in a different direction. So if we want to kind of extract a row in our matrix, we go from the left-hand side, and then we slap our basis vector from the left, and then we multiply one by one vector matrix products, right? We do not do any matrix multiplication, which is a costly computation, but we only do vector matrix multiplications. Okay, so then it looks like this. And so it's basically the reason why it's more efficient. It's very efficient just collapsing the dimensions one by one. Instead of if you were, so it's something we might do in the exercise that we compare what exactly is the number of floating point operations that you need to do if you compute the matrix product first and then add the vector, or you do this with vector matrix product or matrix vector matrix products. Yeah. All right. So excellent. Okay. So basically, so what we extracted now is that using matrix vector products and vector matrix products, we can characterize product of matrices completely lossless in a fully efficient form. And we never need an explicit representation of any of the internal matrices. So we never needed, so none of these internal matrices that we have to have like a table, right? And we only needed to have like a black box, like a program that we stick in a vector and it gives us the matrix vector product. Or we stick in a vector and it gives us the vector matrix product. Okay, so this type of approach to compute products of matrices by extracting rows one by one or extracting columns one by one is sometimes called the matrix-free approach, because you avoid having this explicit representation of a matrix, and by that you become much more efficient in computing these things. Okay, so now let's go back to our derivatives. So basically our main job is to kind of characterize the product of the Jacobians, right? So what we want is we have our program which goes through multiple transformations, f, g, and h, and we want to have the partial derivatives of that. And we know, okay, because it's a composition of multiple functions, it's going to be a product of Jacobians, right? And so now what we basically learned from this entire discussion is that we can compute, by just having the vector Jacobian product. So now I say vector Jacobian product because it's a Jacobian matrix, but it's the same type of deal. So by either having a vector Jacobian product or Jacobian vector products as functions or as programs, we can completely characterize the full Jacobian end-to-end, without ever having to explicitly write down what the full Jacobian is, right? And so the reason why this is important is because you can imagine, okay, in deep learning, you have billion parameter models. And so let's say you have a multi-layer perceptron with like 1 billion parameters and like 1 million inputs. It's a huge weight matrix, right? And so very often it's very sparse. And so this is exactly where you win then. Okay, so let's try to do this. Okay, let's say we somehow magically somebody gives us the function that computes the JVP or the VJP for f, g, and h. So how can we compute the derivative of this program? So we can do what's called forward mode differentiation. So we go kind of from f to g to h, so in the same order as in the program. So that's why it's called forward mode. And so we know that basically the only thing that we're supposed to be doing is to do like the Jacobian vector products one by one, right? And so we know, okay, we have the Jacobian vector product of f on the input vector, and so that gives us our output. And then we stick it through the next Jacobian vector product, the next Jacobian vector product, and finally what we extract is a column of the Jacobian, right? So this program is exactly the type of construction that we had here, right? So we had our Jacobian vector product once, twice, and 3 times, right? But we can express it now as a computer program, which is very nice, right? So and you will notice the composition is exactly the same thing. So you compose 3 functions, and then here you compose 3 functions in the same kind of structural order, right? And so that's important. And we'll come to this later why this is important. Okay, the other direction is also interesting. So we can extract also a row of the Jacobian, which is just, okay, instead of using the JVPs, we use now the VJPs. And so what is happening between the order of operations between the main program and the gradient program? Anybody have notice a pattern? Yeah, it's exactly in reverse. So instead of going FGH, we go HGS, right? And so that's why it's also called reverse mode differentiation, because we just go from left to right instead of from right to left, right? And so right to left is the early operations come first, and so that's exactly the same type of order that we have in our main program. And in reverse mode differentiation, we go from left to right, which is exactly, we do the late transformations or the gradient computation that corresponds to the late transformations first, and then we kind of work our way backwards. Okay, so let's see then. So how do we then actually extract this? So one thing that you might imagine is, so let's say you have some magic box that as you're running through the program, not only does it spit out the result of this function, but at the same time it also spits out this Jacobian vector product function or vector Jacobian product function. So let's say, okay, let's start the program. So we're saying in Python, okay, go. And so what is happening? So the first thing that needs to happen is it needs to compute f of x, right? And so that will compute a. But now let's say we have a function that also, as we're computing a, it will also give us the JVP kind of black box that computes just the Jacobian vector product as a secondary output, right? Okay, so then, okay, we just kind of collect this, and then we go to the next step. Now we compute g of a, so it's a new function, and now we it produces b, but at the same time it produces an like auxiliary function which is the Jacobian vector product, but for the transformation g, right? And then we go further, and so like every time we go through like some kind of microscopic statement in our program, it not only produces the output, but it also produces an additional function that we can use later on in order to do gradient computation. Okay, so just to repeat, so we had our program, we start doing our computation, and as we're computing, like it will just spit out these additional functions. You could also think, okay, maybe it's just a compiler, and like it compiles the program and it sees, okay, first there's F, then there's G and H, and the compiler will kind of define these functions for you as it's compiling the code, right? So there's multiple ways to think about it, but somehow it's inspecting the code either while you're running through it or by just looking at the code, and it will produce these additional black box machines that implement the matrix vector products accordingly. Okay, so then once we have this, so let's say we run this function, we're just collecting all of these, like this bag of JVPs. So how do we construct the gradient calculation? We just take all of these things and we put them together in like an overall function that gives us like a column of the Jacobian of this entire program, right? So by just collecting these things and assembling them in the right order, we can write very mechanistically, without thinking too much, a gradient, like a program that computes the gradient, right? So why did you not have to think so much? Because you're just kind of putting the lines of code exactly in the same order as they were in the original program, right? So it's not very complicated. Okay, so then, so that's how you can, produce a kind of gradient program, and it's kind of like a shadow program. So you have your main program that you might think about, right? You write it, and then some system is generating this additional program in the background, which has a similar structure, but it's, its job is to compute the derivatives. Okay, so let's see how we can do this then with our VJPs. So now we do the same thing. And so now we go kind of from our programs, we have H, or we have our VJP for F and for G and then for H, right? And so now, but now we need to kind of take a little bit of care, and then we need to, when we're assembling them, it's still mechanistics in the sense that it's not complicated, but we just need to think about it a little bit more. And we need to go kind of the opposite way around, and then we can basically go H, G, and F. And this is our derivative program in order to extract the row of the Jacobian. Okay, any questions so far? Everything clear? Okay, it's not super clear that this is easier now. It's, I mean, it's kind of more formalizing the way how it's kind of how you can compute it efficiently. Right now, it's still, okay, who's doing this for you? Okay, so basically what we want, but okay, let's imagine we have a system that we have a function that maps from X to Y, and now we have a system that has two outputs. Instead of just having the Y as an output, it also has like an additional function as an output, in which you can stick in a vector and you get a vector out, and that's your VJP or JVP, and then we can basically blindly assemble a gradient calculation for us as we want. Okay, so then the next step is, okay, so okay, we went through this multiple times, and we always talk about VJP and JVP, and it's very confusing or easy to mix up, but it's important to have both of these options, because okay, let's think about which option do we want for machine learning. So for machine learning, okay, what gradients are we actually interested in? For machine learning, we're basically only interested in having a gradient for our overall expected empirical risk, right? So we have our empirical risk minimization, which is expectation value over all the data sets or the data instances for the specific points of parameters. And then we have our overall loss function as as a function that kind of maps from the parameters to the overall loss value, right? And so in the neural network, we have many, many parameters. And so we have the input space is very, very large, and the output space is scalar, right? So there's like a single number that characterizes the performance of the neural network, and we want to minimize that number. So what we're interested in is the gradient with respect to phi, which is high dimensional. Okay, so then what does the Jacobian look like? So the Jacobian looks like a single row, right? Does that make sense? Because so we said, okay, how many? So the Jacobian is like all the partial derivatives of the output coordinates with respect to the input coordinates. And so the output coordinates, so this is the rows, and there's only a single output, and so that's a single row. Okay, so then this makes it clear, okay, which type of differentiation do we want to do? Do we want to do forward differentiation or reverse differentiation? It already says on the slide you want to do a reverse differentiation. Why? So let's imagine we have like 100 million dimensional input. Okay, if we wanted to do forward differentiation, how many times do we need to run this? This type of thing. Oops. Where's this? Okay, how many times do we need to run this? If we have like 100 million input dimensions, we need to run it 100 million times, right? And so if your forward program, let's say it takes like a second, right? It's a fast program, but then you need to run it 100 million times, it becomes very, very slow. And you can compute exactly the same thing by just reverse mode differentiation by just running once. So you just do one backward pass, and then you have extracted the entire row, which is maybe 100 million dimensional long, but it's fine. You only run this once, and then you have extracted the entire row. And so that's already pretty good. And so that's why for machine learning, really what we want to do is reverse mode differentiation. And okay, so this is essentially what enables kind of machine learning to scale to billions of parameters. So all of these kind of cutting edge machine learning systems, in our exercise with a neural network with 9 parameters, right? But here we have billions of parameters, and so you need to have a billion dimensional gradient, right? Because why do you need to have a billion dimensional gradient? Because you're in a billion dimensional space of parameters and you want to somehow optimize in this space. And of course, you have zero clue on where to go, except that you want to have some local information, right? So this is what we had with the loss landscape, that you don't have any, you have no idea what's going on. But if you have local information, at least you can go locally kind of downhill, then you can actually efficiently optimize. But this requires you to have like a billion numbers in for your gradient. And so if you were to do like a naive implementation where you kind of implement your neural network in Mathematica and say, okay, give me the derivative, and this is not going to work. And so that's basically what the magic of this type of reverse mode differentiation is. And so here now, okay, I say billion, but by now you have like a trillion dimensional model. It's kind of crazy as physicists, when you kind of do like a statistics course, sometimes people think about, okay, I'm doing like 100 dimensional fit with like 100 parameters, right? And then that sounds already complicated. But here we're basically doing optimization in a trillion dimensional space, which is completely crazy to think about. And so this is why I put the quote of Geoff Hinton, which is one of the kind of pioneers of deep learning, as basically, okay, how do you imagine a high dimensional space? You just kind of imagine a 3-dimensional space and tell yourself that it's actually a trillion dimensional space. Okay. maybe one aspect to this. So why is there this kind of distinction between what, as physicists, we kind of feel, okay, 100 parameter fit is complicated, and so machine learning is doing a trillion parameter fit. So what is the difference, right? And so the difference is that for us, when we do a statistical analysis for like some kind of data set and we try to fit it with some parameters, usually these parameters have a very clear reason to be there, right? So they might be like a mass of a particle or like some interaction rate or something. There's like some physical reason what this thing represents. And we like to think that our nature is simple, it's compositional, there are simple rules, so on. And so we don't want to have a world where we have like a billion different rules, right? And so, but what's the difference with machine learning? If we go back here, so what do these parameters actually represent, right? So the parameters represent the number of, in some ways, kind of the number of linear regions that you have in your function, or like the number of corners that you have. And so let's say you have like a circular thing, so it's conceptually like an easy shape, but you need many, many little line segments to approximate it. So it's not surprising that even to learn something simple, you need to have many parameters. So in a way, it's like a what's called like a non-parametric way to learn a function, a non-parametric way in the sense that the parameters don't make physics sense, but it's, you know, you just kind of have, you know, lots of kind of equal components that add up to some complicated shape. Okay, so that's why kind of as physicists we're confused by many you know, like 100-dimensional fits, and then but then we don't really care in machine learning. Okay, let me try to. Okay, so excellent. So and so in machine learning, this is called, so you might have heard about backpropagation. And so backpropagation is exactly this type of system. It's what we call reverse mode differentiation. Is now backpropagation. And what's kind of interesting is the history of machine learning. So machine learning, because machine learning didn't really develop this type of overall concept of kind of forward mode and reverse mode. Why? It's clear, you know, to understand why, because the only thing that they were ever interested in is like a single row Jacobian, right? And so the only thing that they, like machine learning as a community, found is reverse mode differentiation, which they call backpropagation. And so this is one of the seminal papers from Jeff Finton that really kind of enabled us to train kind of deep neural networks. And they had a paper in the 80s called Learning Representations by Backpropagating Errors. And so in the machine learning literature, you'll find this being called backpropagation, but important to understand is actually backpropagation is a system like of a general setup of automatic or algorithmic differentiation, right? Where you can go forward, you can even do mixed forward and backward differentiation, doesn't really matter. And so kind of from that mathematical side was developed already in the 60s and 70s, but you know, the paper was written and finished, so okay, maybe that also played a role. Okay, so then the next step is basically, okay, you might ask, okay, we basically developed all of this structure for like linear programs. So programs that are like a very trivial type of composition. We have, you know, f of x, and we stick the result into some g, and we stick the result in some h, right? And so, okay, we what we promised is that we would have like some differentiation for arbitrary programs, right? And so this is not an arbitrary program. Okay, what you might think is, okay, I can basically add as many compositions here as I want, and it doesn't really matter. I can just do the same type of construction and I will be fine, right? And depending on what the input dimension and the output dimension is, I can choose, okay, do I do forward mode differentiation or reverse mode differentiation? And that's fine. But really, you know, kind of realistic programs, they kind of look more like this. We have like control flow, we have loops and so on. And so the question is, okay, how do you do a differentiation like this? And in order to do this, basically what you can do is we can try to get a hint of by kind of looking at matrix multiplication as like a graph computation, right? So let's say we have our graph computation. And so what is the output of our first matrix multiply? So we have our 3 input dimensions, and then we have a 4x3 matrix. And so the output dimension is going to be 4. So there we have 3 inputs, 4 outputs for the first step. And then we go from 4 outputs to 2 inputs, to 2 outputs later on for the second matrix multiply. Right. And so you can basically write it down a little bit like a neural network. So this is not necessarily a neural network, but you can just describe this matrix multiplication as a graph. And how many edges do you have? So you have, like the matrix has 4 by 3 entries. So you have 12 entries. So that's why you have 12 arrows. And every arrow is basically pointing to every, so from the input to the output, right? And so you can do the same thing. And then for the second matrix multiply, and now you have 2 by 4, so 8 arrows. But it's a kind of exact one-to-one map. And so what is actually, where are the matrix entries here? So like the individual like MIJs. The MIJs are the edges in this graph. They are kind of associated with some kind of value. And in order to do the matrix multiplication, you need to take the value from the edge and you multiply it with the input that is at the node, and then you get the output. Okay, so then what we can look at is basically, okay, how can we do, okay. So how can we do vector matrix products? So in the matrix picture, the way that we do vector matrix products is, okay, we have our vector and then we have our matrix, and we need to sum over the index that is kind of where they're next to each other, right? And so it's just one sum. It's standard matrix multiplication, right? And so how does this correspond to like the graph picture? So let's say we want to compute kind of our value y, and the value y is the like is a function of the matrix, which are all the edges that connect y and z, right? And so which edges are important? Actually, the only edges that are important are the edges that end in y. So it's the edges that end in in this case y2, right? So these are the only edges that are important, right? And then you have basically 2 edges always for every output. For every y, you have 2 edges that connect to it from the bottom, right? And so basically the way that you can say, okay, you can basically sum over all of the kind of edges that connect your y to the z's, and then that's the way that you do your vector matrix product. How do you do this in the other way around? So let's say, okay, whoops. So let me see. Okay, there's a error here. Let me try to fix this. Okay, so this is okay, let's do something like this. Is that right? Oops, okay, nope. Let's have something like this. Okay, now it should be correct, right? Okay, so basically we have our matrix vector product. So we have our matrix first and our vector first, and then which edges are the only important edges? All the edges that have this output index kind of as part of their edge, right? And so you say, okay, only the parents of y are the ones that really contribute to this value of this matrix vector product. And then you basically do like a weighted sum of the inputs weighted by whatever weight is on the edge, right? And so you can do a matrix, so you can generalize matrix vector products and vector matrix products to graphs, right? Without any issues, exactly the same type of construction. But now what you have a freedom that you don't need to have a graph that is fully connected like this. We now formulated this idea of a matrix vector product in a way that only talks about the graph, and it doesn't talk about matrices anymore. And even though we might still call it matrix vector product, there's no matrix anymore anywhere, right? Okay, so then with this graph picture, basically we can generalize like all of the stuff that we've done with differentiation and forward and backward and so on. We can basically generalize this to arbitrary computation graphs. And so what is a computation graph? A computation graph is nothing else than a program, right? So like if you have like an expression, like a mathematical expression, you can always express some mathematical expression as a graph of operations. And then once you have a graph, you can use our kind of definition of vector matrix product and matrix vector products, and then implement your efficient way to do differentiation. Okay, so basically, we talked a lot about kind of how to do this, but okay, the question is still who is doing this for you. So we have this kind of strategy, but we don't want to do this ourselves. There's no need that we need to do it ourselves, because in any case, this is just more or less just mechanically putting together all of these kind of different pieces, and we know how to traverse the graph and what the type of computation is, and we just there's some kind of simple rule to do it, and it's definitely something a computer can do for us, and this is what leads you to this field of automatic differentiation. So automatic differentiation is a third way to do derivatives for programs. So what is like a simple way to do derivatives of a program that you might have used in computational physics 101? So if I told you, okay, what's the definition of derivative kind of in mathematical sense? Right. Right, exactly. So there's basically, what you can do is you can, let's say, compute a function here, you compute a function here, you have two different values, and then you kind of divide this by the distance of the input values, right? And so then you need, so how many evaluations do you need for of the function for every kind of partial derivative? You need 2 evaluations per coordinate, right? And so if you have 100 billion coordinates, that's not going to work, right? Because then you need 200 billion evaluations, and at the same time, also because you have these finite differences, you want to evaluate them close together, and it's going to be numerically very unstable. So so this is called numeric differentiation. It's not an efficient way to do machine learning because it just doesn't scale. So, and then we already mentioned that we also have what's called symbolic differentiation, which is basically you put it into Mathematica and just let it use the chain rule and so on. It will basically also produce an expression for the derivative. And so now it's an interesting question. Okay, what's the difference between this and automatic differentiation? Because both use the chain rule, right? Of course, and it's not like automatic differentiation came up with a very, like a magic trick to do kind of derivatives. It's still the chain rule, but the kind of secret sauce of machine learning or of automatic differentiation is that it will reuse the structure of the program exactly as it is in the input program. That's going to be a very efficient reuse of computation. So you might have seen, when we did the gradient computation for our multilayer perceptron, there's many things that are kind of computed multiple times. So there's grad sig times grad x. This is used multiple times. And so if you were to do backpropagation, this would be stored in a variable, would be reused multiple times instead of kind of computing it, the same type of expression multiple times in separate steps, right? And so this is exactly what symbolic differentiation would do. It will basically just express everything, just expand everything, and then all of these subterms are going to have like a similar structure, and it's just going to be super inefficient. And so by just co-opting the structure of the program in order to also implement your derivative program, this is then a way how you can be more efficient. Both use the chain rule, both are exact. The gradients that you get from automatic differentiation, there's no kind of approximation involved. There's an exact gradient, at least to the precision that you can get it with a kind of computer. But then, so it's exact, but it's also efficient, which is not something you can say for the symbolic differentiation. Okay, so then you might have heard about these names. So who has already used TensorFlow or PyTorch or JAX? Anybody? So, okay, a few of them. So if you already have used these things, you might know them as machine learning frameworks. But really what they are at their core, they're programming languages, and programming languages in which you can define programs that are automatically differentiable. So you just write a program and you tell the system, okay, give me the gradient, and it will give you the gradient. And it's just a programming language, right? It's like a programming language with superpowers. And so let's see how this works. But before that, so these things you might know as machine learning frameworks. And so there's lots of like machine learning things, but at the core, they're differentiable programming languages. And kind of independently from machine learning, I already kind of hinted at this, that machine learning kind of, they rediscovered the backpropagation on their own, and somehow was independent of an entire other branch of computer science and mathematics that already had these types of differentiation methods. And so there are also packages, for example, in order to make C++ code differentiable or Fortran code differentiable, which is not something that you would usually have in machine learning. So most of the machine learning frameworks are kind of written in Python. At the core, they are C++, but what you see as a user is a Python. But let's say kind of in your own work, you have like some C++ program that you want to have a derivative of, that might happen in physics. You have like lots of tools actually available in order to compute these derivatives. Okay, so let's see what this looks like. So let's say we have our function. It's a simple function that does kind of two types of composition. So we have two inputs, X and Y, and then the output is also two outputs. And then we have basically like a 2x2 Jacobian. And then in order to kind of implement the gradient computation, we kind of manually define Jacobian vector product, right? And then we compute our Jacobian vector product, which is also just a vector with two entries, because you stick in basically you have a 2x2 Jacobian and a two-dimensional input, and then you get a two-dimensional output. And then you do all these things. And so, but okay, nobody wants to do this on the left-hand side. And now let's see what this looks like with JAX, which is one of the kind of newer automatic differentiation systems from Google. And so here we basically do exactly the same thing. So what is the difference between the function definition on the left and the function definition on the right? So the only difference is that instead of NP dot, you said JNP dot. You could even say import JAX NumPy as NumPy, as NP, and then it would exactly be exactly the same function. Just that like magically, you can get the derivatives out, right? And so you can basically say, okay, give me the JVP of this thing, and then we'll basically give you all the gradients automatically without you doing anything. So the only thing that you did is to define the function in this programming language that is automatically differentiable, right? And this gives you like a path to how to do machine learning in a nicer way. You write your family of programs in the differentiable programming language, and then a gradient descent comes out for free. Okay, so basically, okay, what does this look like now? So let's try to kind of implement our multi-layer perceptron, which we had in the beginning. And you might remember in the beginning, I kind of indicated all the different lines that are gradient computation, which was annoying. And so now we can basically say, okay, it's a much, much cleaner code where basically, okay, we say, okay, we have our linear layer, which is our input and our parameters, and we have our sigmoid, we have our ReLU, we have our perceptron, or we have our multi-layer perceptron, and all of these, there's zero gradient computation that is visible to you. And if you stick this into JAX, so you basically define this program in the programming language JAX, and you can just ask JAX, okay, what is the value and the gradient? And this gives you the value and the 9-dimensional gradient, because we had 9 parameters for this multi-layer perceptron. Every node has 3 parameters, and it just spits out kind of magically a 9-parameter gradient, right? And then this is what you stick into your gradient descent, and then you're happy. Okay, great. So maybe just one more thing about kind of which framework you use. So I would recommend, so TensorFlow and PyTorch are very, very kind of battle-hardened frameworks to use. So if you want to do machine learning, just to do machine learning without kind of trying to do like develop new methods, I would recommend to use either TensorFlow or PyTorch. In this course, we're going to use PyTorch primarily. And so PyTorch is by Meta, or what used to be Facebook. So that's the main backer of PyTorch. And then the main backer of TensorFlow is Google. And then the research division of Google developed JAX. It's a type of research language, which is much, much cleaner in the way that it implements automatic differentiation, which where it's less obvious that it's meant to be a machine learning library. It's more like a programming language. And so if you want to work on what's called differentiable programming, and then I would recommend to use JAX. All right, so basically this is already our summary. So basically by far the best way to learn kind of family of functions is through gradient descent, right? And but we know that structure is important, and basically the shape of the hypothesis set is is relevant in the sense that we want to constrain it to functions that we're interested in, and so this is what we call inductive bias. And so that's why we want to go from kind of generic networks, which maybe we can show are universal function approximators, to specialized networks that implement some specific family of function. They implement some prior knowledge that we know the solution should have, right? And so then there's a big trade-off between, okay, how much prior knowledge do I need to stick in, and how much do I let the network learn? Because as we know, if it's a universal function approximator, with enough data, it will learn everything perfectly, right? So that's what it means to be a universal function approximator. So if you have lots of data, you need little inductive bias. If you have little data, you better have lots of inductive bias. And so it's a trade-off, and then there are lots of discussions, okay, which things are important, which things are not important. This is going to be the rest of the lecture. And then automatic differentiation is basically a way to efficiently and automatically compute gradients, almost for arbitrary programs. Okay, so that was basically it. I want to kind of close this lecture with one thing where, which I already hinted at, is that you can go beyond neural networks. So now recently there has been quite a lot of interest in the physics community to write computer programs that are computing like something that is completely unrelated to machine learning, but where it's often useful to have gradients, right? So for example, one of the things is if you want to just do like a statistical fit and you want to minimize the likelihood, it's still using gradient descent, but and so in some ways it's still an optimization problem, and it's a likelihood minimization, which sometimes you can also express machine learning as likelihood minimization, but I mean, we think about it in a different way, right? And so then you see papers like this, and you can see, okay, there was basically like a system where that defines the structure of the proton. What is exactly the structure of the proton? In the proton there are multiple kind of even smaller particles in the proton called quarks, and quarks and gluons, they interact with each other, and so there's no closed form solution on what the true structure of the proton is. So this is something we need to learn from data. And so this is something we can model with kind of very simple neural network. But in order to fit the parameters of this neural network, this neural network was not trained with gradient descent, which is very weird. So it's a neural network that for a very long time, for like a decade or so, was not trained with backpropagation, right? And so why was it not trained with backpropagation? Because the output of the neural network was then stuck into some physics simulation, and this chain was not differentiable. So you could not go from the output of the physics simulation to the parameters in a differentiable way. But now if we kind of implement all of this in a probabilistic, in a differentiable programming language, then we can just compute the gradients end to end, and then we can optimize this. And so it's a very kind of active field to combine machine learning with differentiable physics simulation in order to optimize something, right? And so that touches a bit on, guiding the hypothesis set. So you can also guide the hypothesis set by sticking it through lots of physics simulation. And this is, instead of doing like inductive bias, where you're reducing the solution space to something in between, you can have a much richer evaluation of the output by, passing the output through physics simulation. Okay, so now it's kind of, it's also something that I personally work on a lot, is kind of making physics code differentiable for various types of applications in particle physics. And so I just want to close maybe with this. So this is Jürgen Schmidhuber, who is one of the famous also a little bit crazy figures in machine learning. But he was, also at TUM, right? So your colleague. And so in the 90s, they already wrote kind of a position paper called like Making the World Differentiable, which kind of argued exactly for this type of thing, that, lots of things can be optimized and you want to have like a soft representation of various things. And so now, kind of 2 decades later, this is actually happening. And so we're starting to make like fluid dynamics simulation differentiable. We do like quantum field theory calculations differentiable, molecular dynamics simulation differentiable. And it's always kind of this idea of combining machine learning with physics that is, kind of like an interesting field. Okay, so I'll close with this. Yeah, I think we have some time for questions. I thought we would take a little bit longer time to go through all this math. So if you want to go through it again, we can do that. Otherwise, you have some time to kind of, so yeah. Sorry? How JAX? Yeah. So that's exactly this thing. So basically, here, so the way that you would use JAX in like your in the real world is you would use something like this. You would just take, okay, give me the value and the gradient of this function. So you say you have a function, right? Multi-layer perceptron. This is my function here, and it has 2 inputs, x and parameters, right? And so now what we say, okay, which gradient do we want? Do we want to have the derivative of the output of the multi-layer perceptron with respect to x, or do we want to have the gradient with respect to parameters? So for machine learning, what we're interested in is we're interested in the gradient with respect to the parameters of the perceptron, right? And so that's why we say, okay, we wanted to with respect to the argument 1. So that's like it's zero-based counting. So x is 0 and parameters is 1. And so then basically we ask JAX, okay, give me the value and the gradient from this thing. So, but then, okay, what does it do kind of in under the hood? Under the hood, it does exactly this type of construction. It will basically analyze the program by running it through the program and kind of doing a little bit of bookkeeping. It will run through the program and see, okay, now you're hitting F, now you're hitting G, now you're hitting H. And so it will produce these kind of little functions that implement the vector Jacobian product or Jacobian vector product for whatever this function is. So it might be sine. So and if you make the kind of individual functions kind of as atomic as possible, so if it's like a sine or a cosine and so on, at these points, so you're basically hand coding what the true derivative is, right? So we know for sine the derivative is cosine, right? And so then, but then once you have this, and we know for like a product, like a product of 2 numbers, we know what the product rule is for derivatives, right? And so for like the binary operation of multiply and for the unary operation of sine, we can kind of hard code what the gradient is. But then suddenly, once you do this, suddenly any type of composition of sines and multiplications becomes completely differentiable, right? So you only need to have like a list of individually implemented hand-coded derivatives for like atomic, like core operations like multiplication, addition, exponentiation, powers, like trigonometry and so on. And so once you have like this basic set of functions, then you can basically do any type of composition between the two, and then you have a derivative, right? And so this is exactly what JAX does. It will basically overload all of these different things. And so that's why when you write this thing, and basically, so here, what is happening here? So here you have like y to the power of 3 or x times y. So, but what is being multiplied here? On the left-hand side, what is being multiplied is NumPy arrays, right? And multiplying NumPy arrays doesn't know anything about differentiation, right? But on the right-hand side, what is being multiplied is JAX NumPy arrays. And so JAX as a system knows what multiplication means and will kind of trigger this additional extraction of this JVP or VJP function that is appropriate for multiplication, which is just a product rule, right? And yeah, and then it basically just does this type of composition that we did here by hand, kind of end to end. Yeah. So basically, so you can say, okay, if you have, let me see, we can do this as an example. So what is so here you have like 2 input nodes and 2 output nodes, right? So you have x and y, and then you have x times y and y cubed, right? And so what is the graph structure of this thing? So the first output, to which input nodes is it connected? So connected to both input nodes because it's a function of x and y, right? The second output, y cubed, is only connected to one of the input nodes. And so it's not a fully connected graph, right? So in the matrix picture that we had here, basically you had, so the reason why it was 1-to-1 to the matrix picture is that it's a fully connected graph. You have as many output, for any input, everything is connected to everything, right? But as we've just seen in this example, it's not the case that everything is connected to everything. And so when it means that, it will basically try to do kind of like a matrix vector product here, it will not use like the matrix vector, like the matrix multiplication definition of a matrix vector product. It will use the graph-based definition of matrix vector product, but it's the same thing. And then you can do the same type of game. So if you have a generic graph, for example, how would you do basically kind of the forward differentiation? You would initialize this kind of computation by 1, 0 or 0, 1, and then you would run this entire graph, right? What would be the backward? And so then the matrix vector product is basically kind of defined by these arrows, right? And then how do you do reverse mode differentiation? You take the output and then you kind of push the values upstream in the graph, right? It's the same, but it's a kind of more complicated picture than what we had in the matrix, but it's very equivalent. So it's basically like this type of picture, right? So you initialize it and then you go like this. But now you can imagine, okay, you only have like a graph instead of like a fully connected thing, but you can always re-express this as a graph, and then you see how the data items flow. Okay, any other questions? Yeah.
So I just try to understand why exactly like propagation has it's just like dimensionality of the Jacobian, but why actually the test?
Okay, so let me see if I can. I mean, you can compute, so it's going to be an exercise. I'll not show it here. But I mean, one thing you can compute is, okay, how many operations do you need for matrix multiplication? So you have a matrix. So let's say you have A times B. Okay, this is not working. Okay, so then we'll leave it for the exercise. So, I mean, try to think about how many floating point operations do you need, and then take like an arbitrary sequence of 3 matrices and just see how many you require. And yeah, so we'll see this exactly in the exercise. Okay. That's it. Thanks a lot. Have a good weekend, and see you on Monday. And we'll actually start using machine learning frameworks for some stuff. All right. Bye-bye. So we have one question maybe before we stop. There's one question Is JAX compatible with parallel computation and GPU devices? Yes. So one of the nice things about JAX is that it's very nicely compatible with GPUs and parallelization, even without the GPU. And so this is, we will probably not have time to go through this in the lecture, but I encourage you to check it out. And it's called JAX VMAP. It's a great thing. Yeah. Okay, thanks for the question. Okay, bye-bye.